Welcome to the special Digital Futures World Young, or Digital Futures Young presentations on space architecture. These are presentations by young scholars, by students and recently graduated architects. And we're following on from the session that we had a few weeks ago on space architecture by looking at the same kind of question from a student perspective. I'm delighted to be joined today by my colleague Madhu Thangavellu, who was part of that presentation a few weeks ago, and one of the great authorities on space architecture, an architect who's worked his whole career in space architecture. Today we have 7 presentations. I'll introduce these briefly, the student presentation briefly, and then I will go on to say just a few words to frame the discussion itself. So I want to start off then with our first presenter, Aries Wang, who is a graduate of Dessau Institute of Architecture, DIA in Dessau, Germany, where I myself used to teach some time ago, and where Sina Mustafavi is now teaching. She is now working at TU Delft as a researcher in the robotic fabrication team and working on certain items for the International Space Station. Next, we have a team from Shanghai in China, LAC Studio, that's led by Dan Liang. She's a graduate of Shanghai University. She then went on to study at the Bartlett in London and received a distinction for her work there. She was part of Digital Futures a few years ago. She then came back to Shanghai, worked for the Design and Innovation Department at Tongji University, and now she's working as an architect in Shanghai. Part of her team also is Chen, who is a graduate of Shandong Normal University in Shanghai, and Lulin, who is a graduate of South China University of Technology. Then our third presentation will be by Levant Ozruh, who is a graduate of, first of all, Edinburgh University, and then the Bartlett. He went on to work for Carl Ratti in the Sensible City Lab, Corp Himmelblau, and now he's a unit master in the Bartlett. After that, we have Selin Sabin, who is a computational designer, studied at Istanbul Technical University, then at Lund University, and now working as an architect in Istanbul. She was a winner of a prize for the Mars 2050 Habitat Design competition. Then we have John Hatcher from the University of Virginia, who is a designer working at VMDO Architects and a member of UVA's architecture robotic research group. He was a graduate Then we have Luis Orozco, who took his M.Arch at Taubman College, University of Michigan, where he taught an intro to robotic fabrication. He went on to work with HKS Architects in London, and now he's undertaking a PhD at ICD Stuttgart. And finally, we have Albert Elias, who was a graduate of FIU, Florida International University in Miami, where he's now teaching as an adjunct professor. What I'd like to do today is to just then move on and just say a few words that come out of the AD on space architecture that I edited. And what I want to pick up on is the range of approaches you get in space architecture. One of the things I'd say is if you are literally working on space architecture, if you're working in the industry, as people like Madhu have been doing for some time, you would know how exacting the whole world of space architecture is. It is a very restrictive zone, and the things you can do are very limited. And I want to sort of match that with the kind of student imagination that presents itself in some of the projects which I showed in this space architecture AD. So just to kind of say something briefly on this project that Madhu knows very well, a project we collaborated on, working for NASA. It was a NASA Innovative Advanced Concepts Research Fund winner. And it points out exactly how challenging it can be to actually work in space if you're being serious about it. What you can see here is a 3D printer that is on what's called an athlete rover, and it is printing a structure on the moon. First of all, why would you want to print a structure on the moon? Why would you want to get a robot to do it? Well, one of the points about living on the moon or living in space in general is that the conditions there are not exactly very hospitable. Radiation is so severe on the surface of the moon. If you went out without protection for more than 7 hours, it is said, you would die of radiation. Not only that, but you have an extreme range of temperature on the moon from almost absolute zero up to about 200 degrees centigrade. The conditions are far from hospitable. And why would you, what it's doing here is printing a structure out of concrete that is based on regolith, regolith being the fine powder, graphite-like powder that you found over coating the surface of the moon. It's printing a structure out of that. And the question would be, why would you want to print a structure out of that? Well, the reason is it's so expensive to send materials to the moon. The figure I heard for a single brick was somewhere between $200,000 and $2 million. It is too expensive to send anything to the moon. Therefore, you are working the concept they have in NASA is in situ resource utilization, use what is there. But the idea of sending huge structures to the moon are very unlikely. So what you have then is this machine printing here in the background. You've got a regular processing unit. And here in the background also you have these solar collectors providing energy for this project. What are the challenges there? Well, the challenges are that in the moon you have a 28-day cycle, as it were, for one day, which means you have 14 days of without energy. So the idea of getting energy itself is going to be quite challenging itself. And then when you kind of think about it, you've got this robot there that is on the moon. It has to be 100% reliable. What happens if it breaks down? You can't just call an engineer to come and fix it. It has to be 100% reliable. And you're facing enormous challenges there. In terms of the concrete itself, there is some water on the moon, but not much water on the moon. So what we were proposing was something that was using sulfur. You can make concrete out of sulfur. So we had a sulfur project, some kind of concrete that we're printing. Then you have challenges with that because there's no atmosphere on the moon, you can't pump it. You have to somehow, using a spiral system, be able to eject it. You've got extreme range of temperature, as I mentioned before. And you've got the very basic problem that you have with any concrete of any kind. You get, not only does it necessarily come out as you project it, also you get something called slurry, which is a kind of very thin film that coats anything with which you might use concrete. So in other words, the challenges of working on the moon are absolutely extreme. If you keep to the restrictions themselves, you're very limited as what you can do. This was a myth. You would not have an astronaut checking these things out. We were doing this as an advert for a promotional team that we expect to get some funding from a company making fabrication technologies, and so we have the situation whereby if you keep to the restrictions of the room of working in space, you are very limited what you can do. In terms of the student projects that we showed, there was, for example, this one from the center at the University of Houston, where they are very seriously pursuing the theme of space architectures, the master's course dedicated to this particular kind of to this program. But you're limited. You get things like spheres, cylinders, and so on. It's extremely restrictive. The alternative is to say to let your imagination run riot and have a kind of design fiction proposal. And we finished off with our student project with this fabulous presentation, which you would have seen on the poster, by Will Hasikian, who was a student from RMIT who was studying at SciAC at the time. And while it is full of the imagination, of course, it's completely unrealistic in many ways. Madhu will be seeing this project next week in a presentation that he's part of. So there we have it. We have this kind of a world which is incredibly restrictive, incredibly difficult to work in. At the same time, you have a kind of domain that fires the imagination. There's nothing like space to kind of really to ramp up things in people's imagination at the moment. And of course, we're talking at a time when there is so much happening. We're hearing almost every day on the news these days. We're getting the Chinese have sent a lander to the moon to collect samples. The Japanese have brought back some samples of an asteroid. We've had Virgin Galactic announcing yesterday they're going to start their space tourism project. We've had Elon Musk with SpaceX, with various projects, the International Space Station, and testing out a lander just a few days ago, testing out a rocket a few days ago. So we're in a moment of acute fascination with space. And yet for architects, the challenge is, do we go for something very literal, or do we go and use it as a space for the imagination? We'll see today a range of projects that approach this from a range of different sort of viewpoints. But I'm very glad to have such a talented array of students today. We have just 10 minutes each. We have 7 presentations, which is quite long. And once we finish those, well, I will invite Madhu to be part of a panel discussion about the presentation. So we'd like to start off then with Aries. Let me stop sharing my screen so you can share yours.
Hello, can everyone hear me? Hi, I'm Aries. I just wanted to share something about my background. I developed sketching skills since I was 5 and fascinated by space exploration also when I was 5. There's a book that my dad gave me for the first time for astronomy. So I don't know if my dad know what I'm doing here, but yeah, so today I could show you that. Hope you like my presentation. And currently I'm a commercial architect in the daytime, and at the nighttime I'm a researcher in Delft currently. I also the members of a seed team led by Angelo Lulin, which is the previous NASA commanders for high seas mission and as a collaborator. So yeah, right now I would like to share my project. So Project Mars House. Throughout the decades, we know that Mars has a pretty good content evidence to support life. So in my project, it's more into biomimicry and learning from the nature and sort of putting into computational aid and iteration. And my project divided into 2 phases. The first phase is on Earth, robotic fabrication on Earth. The second phase is on construction on Mars, robotic construction on Mars. So I want to talk about a little issues for our current space exploration. So as you can see in this graphic is, oh, wait. As you can see in this graphic is showing the current system of the space station. And if you're talking about long-term space flight, there will be, it's kind of unpleasant for astronauts to live in such a chaotic wirings and sort of a 70s technology. So my proposal is, what if we learn from the nature? So as you can see the second graphic in the right, it's about a circuitry system and transpiration system. I always inspired by the transpiration system of how plants work. As you can see, rocket pretty much, the recent technology of rocket pretty much reflected in human bodies, engines like hearts and livers, and it actually provide a lot of weight contribution to space exploration, space flight. But what if we can look into the technologies of a plant itself? A single leaf can do 5 complicated process. So I was very inspired by the Plantier system. So of course, some Mars data and facts. And I was privileged to work with Mr. Angelo. He's my supervisor for this project. So he did share a lot of practical input and also a lot of individual personal pictures and how he lived in high sea missions. It contributed a lot of fruitful practical issues for me to consider. So as you can see in this presentation, the location that I selected is Valley Maninaris. As we know that NASA have a saying like, if you wanted to find life, follow the waters. So this location provides evidence of ancient water flow. So Valles Maninaris is the location I selected. So the form of the structure is actually derived from the SpaceX Falcon Heavy fairing. So the whole architecture, it's sort of forming through the limitation of the rocket fairing. So the structure is very much into inflatable structure, as I really see potential like companies like Bigelow driving their ideas to the future. So inflatable structure is very potential for space exploration. So as I told you, I sketch. So I was sketching, and before going to more deep into space, first you must understand human ergonomics. So I was always inspired by Leonardo da Vinci's philosophy. So he was saying the workings of human body is the analogy of the workings of the universe. So I learned a lot from Mr. Leonardo da Vinci in terms of human proportion. So this is also an idea sketch by me. So it's a flexible membrane, as you see in this picture. And in the right side, it's about the activities actually done by the astronauts. So 7 hours sleep, 1 hour's hygiene, and so on and so forth. And in this illustration, as you can see, it's illustrated in blue colors, and it's actually representing sleeping activities. So it's also a potential for virtual reality. I'm working with a group of scientists from UK, United Kingdom. They're actually developing a smart wearable that can hack into human brain. So when you get the data from a human brain, you actually can control certain membrane or flexible wearable. So in this case, talking about long-term space flight, there's different gravity in space exploration. So we don't really use chair, we don't really use table. So I was thinking this idea of flexible membranes is also to save space. So astronauts are pretty somehow need to, to save space in order to, and in this membrane, it actually gives a flexibility for astronauts to move around the space in this limited space, and also with the idea of virtual reality. So this is the second sketches, as you see. It's rate, and it's actually portraying a work activities. So the first one is the smart membrane. So as you can see in this suit, you can have these point clouds, and actually you can control the membrane according to the activities in virtual reality. So it's also very healthy for astronauts to move around in a very limited space. Just imagine like the movie Matrix, but the difference between the movie is the humans are able to run virtual reality, but not in a body motion way. So this is a little bit like a matrix, but allows body motions to flourish. And the second one is a smart suit. And actually it's like a set of development for the whole Mars mission. And also from this intermediate smart suit is like a second skin, and it can actually act like an additional shell to add on to be a biological spacesuit. This project is also led by Digital Future, High Sci Hybrid Intelligence Sign Matters. So with Sina Mustafawi in this research workshop, if you are interested, you can go into the workshop. And also to understand structure, I came into synergies by Buckminster Fuller. So I was inspired how he sees structures and how he formed geodesic dome. Yeah, and he actually give a very good input, like triangular and tetrahedron is the strongest structure in the universe that we can understand currently. So the form is very much based on the input and the understanding of from Buckminster Fuller. That's how the triangulation, tessellation, it's developed. So you can see in this graphics is showing about the overall section and elevation, how it will go into the environment on Mars. So this is a more detail about the membrane itself. It's a movable membrane, and it has like 1 meters of liquid water or frozen liquid to actually filter out the radiation on Mars. And yeah, this is actually inspired by NASA water walls. If you check on NASA's project, and they are developing some smart membranes called water walls. And also some real-time experiments. So I actually done some I was very inspired by Japanese origami. So in this illustration, it pretty much shows about how I explored tessellation in origami. And the left is more into computer-aided literation, like how do you put it into computational and 3D printed in the KUKA PRC in Dessau International. Oh, I have a little video to share. It's more into like showing how I did for the membrane. In terms of okay, and yeah, this is showing how the form will act in a computational point of view. And also I'm working with Angela Wormuland for SEEDS team. It's actually a project regarding evolving asteroid starship. So it is actually featured in European Space Agency in 2018. You can check it out if anyone is interested. So in this main project of my contribution is how can we grow trees on interstellar mission? Because if you want to talk about interstellar mission, there's you can't depend on artificial life supporting system. So me and Angelo and the team are thinking, how can we grow food and grow trees on interstellar mission? So there's more information into SEEDS network website if you are interested. So the second project with Angela Wormuland recently is Engines of Eternity. It's about sending rotifers to International Space Station and to learn how the rotifers repair their DNA DNA structure. Because if we want to talk about space exploration, we pretty much looking into like regeneration and also understanding the future cultural of humanity. So in this project that we actually send some microorganism to the International Space Station, and then in Florida. So after that, the data returned to Earth. So we have to actually convert the data from the University of Namur and then to form a data sculpture for the coming exhibition. So yeah, that's all for my presentation. Thank you.
Thank you, Aries. So we move on to the second presentation, LAC Studio from Shanghai, and I'd like to welcome Dan Liang to present it.
Oh, could my group member Lulin please share your screen?
Yeah, I need Aries to stop sharing. Aries, can you stop sharing? Okay. Okay. Can you see the screen?
Yes.
Yes.
Okay. Hi guys. I'm Dan. My name is Dan Liang, and I'm an architect from Shanghai. I graduated from the Ballet School of Architecture, and now I'm working as an architect in RSAA in Shanghai, and also I'm an educator in architecture field. So thank you to the LAC Studio. We have this chance to do an international competition about space architecture with another 3 students in China. They are Lulin, Zhang, Chen, and Yuanjun Li. So today I have another 2 group members here. They are Lulin and Zhang Chen. We will do the presentation together for you guys to share with you about our ideas about this space architecture design. So the name of our design is called Infinite Typing. In this presentation, we will talk about this project and also our research about the human and the space. So can you turn to next page, please? Lulin, can you please? Yeah, next page.
I already turned. I guess it's loading.
Okay. Yeah, it's okay now. So I'm gonna just quickly introduce this competition first to let you guys know more about this competition. So actually, it's a real mission, which will happen in 2033. So the LEAP is the first self-sustaining industrial space settlement that will be commissioned by planet Earth collectively in the year 2033. The challenge here is to design a space habitat module for 100 astronauts, and the habitat module will be replicable in nature that can be expanded based on the requirement. So the main functions for this task for the design would be including the mineral extraction and also the research training and processing, and as you see from the screen, also some like production unit and powering unit. So next page, please.
Okay, it's loading.
Okay. So as you see now from the screen, here we have like 3 planets. Yeah, one is Earth, our planet, and also the Ceres, and also the Mars. So for this challenge, the region near asteroid Ceres, located in the asteroid belt between Mars and Jupiter, is chosen. It is also one of the first and largest asteroids known to the mankind. So which means it has a great value for the mining in the space. So the Ceres itself is actually a planet, and its mass is considered to be 1/3 of the total mass of the belt. So the fact is that it will be closest to the Earth on February 2033, according to the prediction. So the mission will gonna take that chance. So the LEAP would be launched for the deep space mission during that period of time. So next part, I will give time to my group members to introduce our concept about the competition, and also our research and our algorithm about design. So Lulin, please, continue.
Okay. Can you see the next page talking about the background now? Can you see the next page talking about the background now? Oh, okay.
Yes.
As for the development of space architecture, we can see that architects passes from some experimental drawing to pay attention to the internal atmosphere of the space architecture. Then, in the recent years, they are trying to apply more advanced technology to space architecture, such as prefabrication, robotic arms. And as we can see, we are a member of the 4th generation of space architecture. What we are trying to do is to locate our project at a greater scenario. That is how we could develop our project from one space module to a larger space settlement, a space city. And in the specific case of our competition, we were asked to design the module specifically tuned for asteroid mining. So we need to find how this mining activity could constrain or facilitate the development of the space settlement. And after research, we decided to focus on the efficiency and profit of asteroid mining. So from research, we get to know that the asteroids can be divided into 3 main categories, which is listed here, the S, M, and C types. The first 2 types, the silicaceous asteroids and the metallic asteroids, contains the prime source of profit for asteroid mining, that is the precious metal. They also contains large amount of nickel iron, which is of no need to be transported back to Earth, but they could drastically reduce the cost of construction for building space settlement. While the C-type, the carbonaceous asteroids, contains abundant amount of water and less useful elements that could be used to sustain life in space. So the starting point of our concept is to divide the asteroids into 2 main categories according to their usage for humankind. The first one is for making profits, and the second type is to sustain life. So what we want to do is to improve the efficiency of asteroid mining by dividing the working and processing work of the asteroids into 2 specialized units. So the 2 units could have their specialized work, but they could support each other as well. As for the finding of our module, we were looking to the microstructure of the molecules, which matches the character of the non-directional universe. So the 2 specialized units connecting by an arm is the original prototype of our space architecture. So for the first type, which is at the beginning of the year 2032, we will launch the first part of our module, which is the arm. It will carry some prefabricated structures and also the first group of space members. One is to find the proper location for the space settlement. It will start building the first construction module. Then the construction module will produce a habitat module. And after generations of iteration, we will finally have a cloud-like space settlement in the universe. So here I'm gonna talking about how we simulate the development of our space settlement. As mentioned before, the activity of asteroid mining are subjected to 2 main constraints. One is to maximize its profit. The other is to satisfy the principle of sustainability in space. So first, as for the developers, they will surely want to build their units at the maximum density. And moreover, once there is already one habitat unit around the potential location to give life support, they would build as much as construction mining units as possible to have more precious metals. However, the principle of sustainability will constrain its development to avoid over-proliferation. So we need to constrain the numbers around one unit to give each of the unit enough space So in our simulation, we set the numbers between 0 and 3. So if the number of units around one potential location exceeds the number of 3, there will be no new constructions. In our simulation, we also add some random elements to simulate the random, the unstable economic station on Earth. And here you can see one possible process of the simulation. And here is one possible result of the final simulation. And in the following pages, I'm gonna introduce more detailed information about our space module. Here is the first part that will be launched in space, which is the arm. On the, I will be faster. On the two sides, it will the rooms that carries the first groups of space members, and while the manning works will be concentrated at the central part, the asteroids taken back by our spacecraft will be crushed before it enters the core and be sorted according to different types to different modules on its two sides. And then when we will build our first construction and mining unit. And I will let my colleague talk.
Hello. In this project, I was responsible for design shared facilities in the living module and the production module. The production module and the living module will realize the transmission and slowly of energy and materials between them with the help of linking device. The linking this is a workflow for all presence and acknowledges fully. Energy is product those complete workflow of presence with the all materials and the values protectional unit module will be transferred from the production unit to the center of the various unit. Next one is running system production model. The mineral raw materials that have been microprocessed on the presence on the are transport to the spiral workflow of the production module. So the nature transport pipeline and then the medicate and wait a minute and then the mineral and then the mineral arm is used for subdivision process. The transmission and display of energy and materials between modules is complete and one time. In order to defend the connect and slowly between each module. Communication.
Hi, Zhang. Sorry. Can I present instead? I think she has some problem with her microphone.
Yeah, if you could just quickly, we need to keep very tightly with our 10 minutes already. Yeah, thank you.
Okay. So basically, in this part, we're gonna talk about our design about the two different modules. Here is a module about the production module, and also could you please turn to next page for Lulin?
Yeah, it's already our turn. Can I see the next page?
Yeah, so another one is about the habitat module. So just like Lulin talk about, she just presented that the two modules gonna support each other and they will supply all the stuff that need to, for example, the fabrication module is gonna supply some like small units for the habitat module. And also for the working routine of the researchers, also some like working routine of the manners is gonna working in the mining module or to the spacecraft harbor through the core and elevators, and also transport it back to the fabrication module. So also we also could use the ARM, I mean the linking device, to solve the some issue for the people to they can get out from the building efficiently from the space architecture. So can you please turn to next page?
Yeah. It's loading.
Yeah, as you see here, the emergency exit will be located on the linking device, and people could get out from the space architecture quickly when some emergency happens. So here is the interior design for the living architecture. Due to the non-direction in the space, so we are gonna have like 3 different boards in the living module, and which could be rotate surrounding the center part to offer like some yeah. So here, as you can see from the center part, it is combined all the different functions, including the access area and the business space, and also the research area. So here is all the diagrams about the different functions which could be combined together to be the center part. So can you turn to next page, please?
Dan, we need to wrap up very quickly.
Okay.
Only 2 pages left, 1 minute. So
here you can see that, yeah.
So we have the 3 boards rotating around the central core of our public function. The 3 boards take different functions, which the farthest from the core takes the work of astronomical observation, while the board in the middle is the residential board, and the one nearest to the core is maintenance and service. And here is a more detailed information about the module design on each board. And yeah, that's all for our project. Sorry for the delay.
Okay, thank you. So our next project is going to be presented by Levant Ozruh. Levant.
Can you see my screen?
Yes.
Hi, I'm Levant Ozruh. I'm from Istanbul. I studied at Edinburgh and Bartlett, and I also worked for Carlo Ratti, Cope, and I was a researcher at MIT. Now I teach at the Bartlett. First, I started as undergraduate unit tutor. Now I teach at the B-Pro program with the Research Cluster 7, where we focus on biospatial design and artificial intelligence. But I guess what sums up my overall interest beyond computational design is divergence and evolutionary design. So how can we create maximum variability? And this project was my final year project at the Bartlett in 5th year. Then I continued developing it for different audiences and projects. But sorry. Yes, at its core, it tries to become the hybrid of contemporary construction techniques such as in situ material reutilization and some of the aspirations that the space agencies have, such as colonizing asteroids and using that material. But also, and as the previous group explained, there's an extensive palette of material source. But there's also a retro aspect to it, which is it goes back to this von Braun wheel and whether we could actually create artificial gravity in space to live. So the project tries to hybridize these two aspirations. One is much more the futuristic one, and the other one, which dates back already to 50s. And this just shows like some of the fictional and prototypical gravity ring radii. But at its core, like my concept is, what if we have multiple wheels that essentially decide on some of the aesthetics of the project, and maybe we create a system of aesthetics beyond everything. So could multiple wheels create some sort of seashell-like aesthetics, and then create a divergence of different colonies? At first, like the idea is the way I introduce material reutilization is, can we arrive at an asteroid and start carving it with small robots? And what we carve, then can we add it on the existing asteroid? And then maybe start to add more like structural elements, a circulatory layer, to then have 3 different wheels, or multiple, in this case 3, and then have a protective shell around it. So this was the very early conceptual exercises, and this was like V1. And then there was some technical, like methodological exploration on what could be the material quality and the inner relationship of pockets and spaces. But then I further developed this, where that generation of artificial gravities could decide on many different layers of the project by a concept of voxelization. So by voxelizing at different resolutions, you could get an exterior shell, then an interior structural shell. But as I previously explained, at its core, the main idea is that we arrive at the asteroid, which is solid. We try to carve out, and we use that material to add on the existing geometry to create something new. So even though here it's kind of simplified, when it comes to the project, there's actually a much more complex interchange of, I must say, Boolean operations. So you subtract a certain shape and then you add it, and there's kind of a whole choreography of doing this. And this is just for one specific design, but because it's tried to be approached in a systematic way, it could be multiplied. And perhaps we could do this with like small robots, agent-based robots. So we would have small swarm of robots which could both carve and print at the same time. So in a sequence like this, we would see that the carving and the construction would be happening simultaneously. So it wouldn't be like we would carve first and then print it, but it would be a simultaneous choreography. And because the robots are inside the asteroid, they would have these charging units on the top. So they would constantly go back and forth to be charged. And maybe the construction scene looks something like this. So in this point, it's kind of a hybrid between fiction, but also relies on some of the discussions on agent-based construction techniques. So it tries to become the hybrid. And the overall result, I guess what I was looking for is that how can it be futuristic or speculative, but have certain sensitivity in its aesthetic and its language, so that it's not too crazy as a form or as a design language. And maybe a bit more on the process and why this could be multiplied. Basically, I've designed everything in a tool called Houdini, which is basically used by the visual effects industry. But some schools like MIT and Bartlett, and I see that more schools do now, have been trying to integrate this to architecture. But what I'm trying to show here is that essentially everything is a recipe and everything is procedural. There's no manual decision making. Everything you do is described. And for that reason, even though you can get into more depth and in a specific version of the project, such as this, we see the rings inside of different layers. And then we see different orientations without the exterior skin to show that the connecting architecture that connects all the 3 wheels. And obviously it doesn't have any orientation, so it looks very different from different angles. Like this thing that in the middle, when we look at it in a naked way, it's actually very different from any kind of orientation and more kind of assembly and layers of the project. But at the end, the thing is like, why not there could be a second one or a third one where it's a system, where we see one of them built from the other one, and this kind of, there's poetics to it. And now this is like kind of the next step, which ties into my research at the Bartlett, which is diverging what I've so far done for just one iteration into a parallel kind of parallel trajectory, where different decision makings are multiplied to different forms, but overall they're the same species, and they're the same kind of thing at the end. They're just in different forms, but they have the same characteristics. And that's it. That's pretty much it. Did I pass 10 minutes?
You were great. Thanks so much, Helen. Okay, let's move on to Selin Sabin, who is also from Turkey. Thank you.
Hey, now I'm sharing my screen. Can you see my screen now?
Yes.
Yeah, great. Hey, I'm Selin, and I'm really happy to be here. And I'm an architect based in Istanbul, and today I will present my master's thesis that I completed at Lund University in Sweden last year. And my research aims to interview biomimicry disciplines and psychological aspects of living in a hostile environment to open up a discussion on living on other planets. And the research question is, it asks how to translate complexity and variety we find in nature for the well-being of humans to prevent spatial boredom and monotony for the intention of creating home feeling on Mars. And it basically has two parts: the research part on space habitability and design experiments on Mars habitat. To start with, space habitability, according to Johnson, human factors has never been the main focus of space habitat design, and this kind of resulted as low habitability. And then Elias presents this concept of integrated design process model that intends to increase habitability by increasing human factors into the design process. And she claims that qualitative factors such as sensations and feelings and emotions could be designed, and this would result as high habitability. And because of these, in my thesis, I focused on the design of senses, emotions, and feelings for the well-being. And these are some important stressors, and its effects on human body to use that. It's really important for me to understand the stressors and its effect on human body. And there are sort of many potential psychological stressors of living on space, and most important ones are spatial boredom and monotony, spatial confinement, isolation, and many that you see on screen. And they have some really important psychological effects, such as like loneliness and depression and apathy and emotional lability. And we could say that human life has evolved in nature, and our bodies expect their senses to be stimulated moderately. And this is what happens in the nature. Color varies, and temperature changes, and the light changes, and the sound changes, and degrees of brightness. And what is missing on space habitats or on other missions is variability of these stimulations. And when there is no change, a state of sensory deprivation happens, and the perception fades away, and psychological problems appears. And that's why we will miss some sort of complexity and variety that we find in Earth's nature when we go on that kind of missions. It was really important for me to set some sort of design principles on well-being. So it's really important for a crew to have this like personal spaces and some sort of different levels of privacy in semi-private, private, and common spaces.
And because of psychologically, because of the limitations, people prefer more complex spaces in confined areas. And to prevent sensory deprivation, stimulation of senses through design is really important. And yeah. To sort of like, maybe this is like a sudden change, but since I will more elaborate on the design soon, I also would like to talk about my site as well. It's Gale Crater, which is located near the equatorial zone, and it has Mount Sharp in the middle, and it has some sort of, it is flat rounded, so it's really important for landing and the fabrication process of the habitats. And based on my architectural principles, I had decided to look for the answer in biophilic design patterns, which bring complexity and order for developing. And differential growth is about how biological systems create forms by varying in growing rates through space and time. And some areas grow more than others, and this leads to some formation of microscopic shape. And as a result, it has a potential to create interesting forms that could be a tool to represent my research ideas and transform into a design. So I have experimented with diverse differential growth principles. What I looked for was creating enough complexity and order in my habitat design to prevent spatial boredom, and seeking the translation of complexity and variety we find in Earth's nature. And throughout my design process, I derive really interesting forms and fascinated by the power of biological forms, ability to bring enough complexity and order at the same time. And at that moment, I had decided to go deep in biomimicry principles and its potential effects on psychology, and create more artistic and cultural approach by freezing factors on air pressure, radiation, and that's sort of like really important factors of living on space as well. So I came to realize those wrinkles, I call them wrinkles naturally, creating intimate spaces when it's needed. And here we see how it's get more complex but ordered, but also it has a potential to enrich the long-term experience. And during the process, I also switched between mediums and play around with the roof and floor with 3D printing experience and to iterate the process. And in the plans, we can see that there are a variety of spaces blending it into together related to the principles, and maybe this would be more we talk about interior circulation of the habitat is designed to prevent spatial boredom in the long-term experience, and the circulation is transformed, made into spaces according to the program needs, with changing heights horizontally and vertically. And outcome of the differential growth algorithm provides a simple base on the ground, yet towards to the upper levels, it gets more complicated and wrinkly, which provides unpredictable spaces to stimulate senses. And because of the logistics, economic and environmental reasons, it is important to use local materials. So 3D printing is the fabrication method. So now I will show some quick sequential images of the fabrication process. And here's the underground entrances built, and potentially drones could scan the site to find matching slope of the steel lab to print on topography. And hypothetically, drones could carry up the slabs to the printing site. And this is a close-up image, and printing continues vertically and horizontally, grows quicker, and that's another close-up image. And here printers start to print transparent plastic roof, which will be filled with water for the protection of radiation, creating connection with outside and getting natural light in. And here is an image from the semi-private workspace, where people have more private space than the common working area, and it's more intimate compared to the common working area, and which is sort of giving a wider perspective to people. And we could see that there are more wrinkles on the bottom, and the wrinkles get bigger on up. And this is where you create connection with the exterior and yeah. To sort of conclude, my research and design phase focused on experimenting with spatial qualities to prevent spatial boredom and creating sense of unpredictability and translating the complexity and variety defined in nature. So that's all I'll talk about. Yeah. Did I exceed 10 minutes?
That's great, Selin. Thank you so much. Thank you. Thank you. Okay, we move on to John Hatcher from the University of Virginia. John, are you there?
Yep.
Jack, sorry.
That's right. Hi, I'm Jack Hatcher. I'm a designer at VMD Architects. I have a Bachelor of Science in Architecture from UVA, and I'm a part of UVA's Architecture Robotics Research Group. I'll be presenting my undergraduate thesis, Printing the City of Ember, and the title is a reference to Gilles Dupros's 2003 book, City of Ember, which is about residents in an underground post-apocalyptic city. So the work was done for Professor Robin Dripp's Future Cities thesis studio at UVA. We spent the first part of our semester refining our questions, coming up with hypotheses, and doing research to focus our time in the one semester that we had. So when I began my research, I wanted to start with the environmental hazards that would inhibit human habitation on Mars. There's very large dust storms, no breathable air, wild temperature variations, and a whole lot of radiation. This chart from NASA shows the high levels of radiation that people would be subject to on the surface. And the background image is a city proposal from SpaceX when they were talking about their BFR. And this entire city would need to be protected either in some sort of metal protection like lead or copper that might be difficult to source there, or it might be water between 30 centimeters and a meter over the entire city, which might be, we might want to use that water somewhere else. And you can also protect with regolith between 3 and 7 meters, which might be difficult to blanket over top of a large city and would limit on how tall you could build and how dense. So I started to look for other options, and in my reading, a lot of people suggested looking at skylights and going underground for that same protection. These skylights dot the landscape around all of Mars's volcanoes. They're formed when the surface collapses into these large lava tubes where lava ran freely for millions of years on Mars and potentially formed some very, very large tunnels. These diagrams depict lunar caves, but the supposition holds that in low gravity, the same basalt structure could form very large spaces. We might not need to fit an entire pyramid underneath, but they might be large enough for a whole city. So looking inside, the ceiling of the tunnel provides more protection than just from radiation. There's a more stable, warmer temperature inside, and you don't have to deal with nearly as much wind and therefore dust. There is no light or air still. There are plans on how to explore these tunnels. This one from Astrobotic Technologies suggests sending down different types of drones and spelunking robots that can handle the unpredictable terrain, charge wirelessly, and communicate back to Earth their findings. And there's a lot of reasons why we'd want to explore these caves. They might be good spots to find life on Mars or water, or just explore the history of the planet further and deeper than we could on the surface. So I'd like to propose boring a small hole down into the tunnel to drop a cable that could raise and lower a 3D printing structure or a 3D printing robot. It might need some extra stabilizing cables. It probably needs a counterweight and probably needs some sort of active tool path correcting sensor system, but there aren't seismic forces and there's not wind, and there's no air resistance. And I feel like it could be modeled and trained to print fairly reliably. it's inspired by robotic systems like this one from MIT's Mediated Matter group, where robotic arm at the end of a crane was used to 3D print a structure in under 14 hours. These robots could be aggregated together by their radii, where the numbers represent proportions based off the radii, and aggregated to leave some central spaces for people to congregate around. Applied to the site, the main point here is just to put them out of the direct sunlight. The skylight could provide some natural daylight to keep people connected to the circadian rhythm of Mars, but that natural or that sunlight would bring all the radiation that we're trying to protect against. As far as what people live inside of, there are concerns of whether a 3D printed structure can be airtight well enough to keep the air pressure that we need. So I'd like to suggest a hybrid inflatable and printed structure. The background image is Bigelow's beam pod that was hooked up to the ISS to test inflatables in space. But the ones that would build the city wouldn't need to provide nearly as much impact protection or radiation protection, so they could be a lot lighter to build and easier to transport. I did some quick collages to come up with different sizes, looking at plan and section, just to come up with some quick sizes so that I could start to master plan these out. These are the center areas in the hexagon grid earlier, where toruses could form large gardens and agricultural spaces for people to focus in on and look at some greenery as they work throughout their day. And that could also be good spaces to introduce artificial skylights as the city builds deeper into the tunnel and more light is needed for that natural connection. So before anything is built, I believe there should be a master plan in place, or just an idea of what we can build down there. There should be an idea of what type of program we want, a typical space syntax, and some zoning heights. But the main point is just that every private residence should have a view of natural sunlight and greenery, so that people have that natural connection to their new planet and know what time it is and stay sane and happy. And then once those pod configurations have been figured out, the 3D printing robots could come in and erect structures into which the pods could link up with and be supported by, and that would grow as the city begins to get built. This is an earlier concept, but it still shows the same idea of pods and a skeleton to hold them up. I think it's worth saying that you could just build a whole cylinder around these things with just slight windows where the pods stick out, but I think we'd still want to save material and time, and especially the binder material that would be needed to bind the regolith together as a stable structure. So there should be some effort to minimize it with designing the skeleton through some sort of topology optimization problem. Looking inside the structure, this is how the inflatable pods could be integrated into the print, where this entire bubble might be contained inside of a more structural unit that gets placed inside, printed on top. And when people start to inhabit the space, they could inflate the spaces, install the floors, bring in all of their equipment, and hopefully install more natural elements. This spot on the left represents the tourist gardens, where they could be good for larger agricultural efforts or just public gardens for people to be able to gather together or just observe throughout the day. This is how artificial skylights could be drilled down using the same boring holes, and that would be used for the cables, where sunlight could be focused down and redistributed with reflections. And that's how I think we could build on Mars. Thank you.
Thank you, Jack. Let's move on. We've got two more presentations. Luis Orozco. Luis, you there?
I am. Let me just begin sharing. Okay, I'm gonna aim to blast this through in under 10 minutes. So, my name is Orozco. Just a quick second to introduce myself before I dive into the project. As Neil mentioned, I did my master's at the University of Michigan, and this was my master's thesis project that I've since developed. But currently I'm a PhD researcher investigating agent-based modeling methods for the use for the co-design of multi-story wood building systems and their civil physical fabrication at the ICD and the Univ Stuttgart. So during my master's at Michigan, I was interested in explicit temporalities. So that's to say, objects are notions that have an explicit relationship with time. So I was curious about chronotopes. And for me, a chronotope is this idea that human work represents the time and the place in which it was made. So the chronotopes that I chose to investigate were cosmologies. When I think of cosmology, when you talk about cosmology nowadays, it's the study of the origin, evolution, and fate of the universe, and is very much a branch of science. However, in previous times, cosmology used to deal with the totality of space, time, and phenomena from the point of view of the human being, and address questions about the universe that were metaphysical and very much beyond what we consider hard science. So this project that I've named Anaximander, the Melontic Archaeon, which I'll dive into, kind of aims to conflate physical and metaphysical cosmology, aiming to both explore the possibility of appropriating the past and existing knowledge, regardless of its relevance, and to try to generate new knowledge from it. It asks, is it possible to expand our cosmology through the use of architecture? Like, it's a framework that, the framework for this investigation is based on kind of a diagram that allows the definition of a cosmology through the collection of artifacts, the organization into taxonomies, and these taxonomies' subsequent embodiment as artifacts again. So cosmologies are usually founded on collections of knowledge, of objects, of intentions, of people, and they all mythically kind of began with experiencing the phenomena we encounter in day-to-day life. In the 1700s, there were cabinets of curiosities. This one in particular is Levinus Vincent's Wundertunnel der Natur. More contemporaneously, we have collections that are equally complex and equally silly. This is the visual storage at the Victoria and Albert Museum as part of their pottery collection for Britain. So in Western tradition, worldviews and philosophies were applied to collections such as these to create taxonomic systems. The kind of archetypical example of this would be Aristotle's 3 base activities of man, which would be theoria, praxis, and poesia, or Carl Voise's 1990 3-domain system for biological taxonomy of archaea, bacteria, and eukarya. These collections are ultimately, and these titles are ultimately arbitrary, but their specificity is as much about the originating culture as it demonstrates knowledge of the objects that are thus classified. I'm gonna skip ahead. We've got tons of crazy examples from that these collections end up being put into artifacts like the Voynich manuscript, or Olaus Magnus's Carta Marina, or Andreas Salarius' Harmonia Macrocosmica. And as the historical time period of these shows, these collections, like this need to create these artifacts was strongly felt in the Age of Enlightenment. And now we found ourselves in the first chapter of the space age, and argue that as we continue to discover and explore, our need to define our cosmology is just as dire as it was back then. One such cosmological artifact has already been made, the Voyager record, with its 116 images and 55 spoken greetings, and we've sent that out. But the artifact that I want to talk about today is Anaximander. So this is our relic. So the title was The Melontic Archaeon. An archaeon is a depot where the archives of a society are stored. Melon is the Greek word for the future. So it means that Anaximander would be an archaeon of the future. It reaches forward as it looks back. Anaximander would house 13 clandestine librarians that regularly welcoming visiting scholars and those eager to access its unique resources. These resources are the program of the space station, which is split up into 3 domains, kind of the past, the present, and the future. So respectively, the archive on the left, the experience chambers, and the telescope. So the archive is the nadirmost component of Anaximander, and it's enormous, 40 meters long, 60 meters in diameter. It takes 6 different launches to get it up into low Earth orbit before it gets blasted off to its final location. I'll touch that later. But it's a perfect time capsule. Artifacts here never age. And seeing as we do from our postmodern perspective, a world not so easily divided into categories, the fact that you have to put things in boxes and put these boxes next to each other kind of enables you to create new knowledge from the juxtaposition. Right? The space is designed to conjure the feeling of getting lost in the stacks of a library, a phenomenon that is as much about the geometry of the space as it is about the adventure of literary discovery. The experience chambers serve as the cloister for our monks. And this kind of ties to what Selin was talking about, sensory deprivation. Each of these chambers has 4 openings, 3 that lead to other chambers and 1 into the surrounding volume. And each chamber contains the technologies and instruments necessary to induce in its inhabitant one very specific physical sensorial sensation. These can be based on our understanding of the senses, but like pain or touch or sight or heat. But like a Borgesian library, each chamber rhizomatically connects to the next, and visitors to the chambers are able to linger or pass through as they wish, fully immersed in the act of being physically and presently feeling. And then finally, at the zenith is the telescope. Like it's a 3-mirror astigmat type telescope, 80 meters in diameter. And right now, one of the biggest questions we have in contemporary science is there extrasolar life? And Mario Livio, an astrophysicist at the Space Telescope Science Institute, is on record for saying that a new, more powerful space telescope to scan the skies of the Earth, to scan the skies for Earth-like planets, we have discovered, in order to physically answer that question, could be possible if it was big enough. Roberto Gilmozzi, the European Extremely Large Telescope, calculated that a telescope of about 100 meters in diameter using adaptive optics would be able to see into the atmospheres of exoplanets. That is the purpose of Anaximander's enormous telescope. By placing it outside of Earth, having no atmospheric aberration, this could be the tool that shows us what exists beyond. So to kind of finish this off, Anaximander is found in Lissajous orbit around the Earth and Sun's second Lagrange point. This is a topo diagram of that. It is here that the fabric of space-time, deformed by the large masses that are these astrological bodies, are flat. So that staying here requires considerably less effort, less force to fight these bodies' gravity wells. In this 70,000 kilometer diameter orbit, 100,000 kilometers before the edge of Earth's shadow, that Anaximander rotates once every 6 months, just outside of the bounds of this shadow, so that it can be constantly heated, constantly working, and can constantly see out beyond. Anaximander was designed to be something we could build today with the rockets we have and the technologies and enclosures we have. By doing small loops in low Earth orbit while during launch and construction, it can then be sent out to its final resting place. And its Lissajous orbit will allow it to be in constant communication back to Earth while still constantly reaching out. Okay, last slide. Anaximander, through its 3 temporal domains, is constantly expanding the edges of our experience, showing us places and things that we have never seen before. At the same time, it has on it examples of our past conjectures on reality, the bestiaries, codices, grimoires, enchiridia, manuscripts, and tones of our understandings past, on which we can build and to teach us how to build a framework for our future discoveries. Most importantly, by having space for the immediate essential contemplation of the human condition in the loneliness of space, introspection into your personal experience is in constant conversation with the societies of the past and the present, and what you see in the telescope of the future. Anaximander is a lens through which to look at the methods we use to locate ourselves within the cosmos. As a framing device for theories of knowledge, itself arranged using these epistemological frameworks, it allows us to focus on the gaps in our knowledge as we seek to expand it. Thank you very much, guys.
Thank you, Elias. That was an extraordinary project. Thank you. We'll no doubt come back to discuss some of those issues later on. So we'd like to move on to our final presentation, which is by Albert Elias of Florida International University. Albert,
hey, everyone. Hi. First, I'd like to say thank you so much for having me. I'm really excited to be speaking amongst a very talented, creative community. Let me just share my screen. Let me know if you guys can't see this. Again, as Neil explained, my name is Albert Elias, and I currently teach computational design at Florida International University. I'm also an alumni from Florida International University, and the project that I'm going to be presenting today is titled Chemicalism. This was my master's thesis project that I took with Professor Neil Leach at FIU, and I describe myself as an information architect, which you'll probably see from the presentation because I'm constantly designing and thinking about data embedded models and what that means at the material scale and how that blends between the digital and the physical realms. So chemicism is basically intelligent design at the level of a molecule. It's covering a couple of different concepts and blending between a few different topics, including organic computing, synthetic biology, and active matter. And essentially what I'm trying to do is using the computer at the computational level to program intelligence into a theoretical and simulated supermaterials inside of a real-time environment. So basically this environment is responding to real-time environmental changes that can be embedded with data. So that would essentially produce an environmentally reactive landscape that serves as both intelligent architecture and a potential future technology. So I describe this project as kind of a proto-architecture, and I call it an ideology because it's not necessarily made directly for humans, and it's more about this potential for synthetic biology. And questioning, is this thing actually alive, or is it more just a procedurally generated system? And so the areas of focus for this project are around intelligent materials and nanotechnology, and studying those at the level of a molecule and how we can operate and design at that scale. And the methodology is through computational chemistry and a real-time physics engine. So in order to simulate some of these topics, I was basically procedurally programming algorithms into a real-time physics engine in order to do the research for the project, which I then output into a final visualization in a different rendering software. So basically this real-time reactive environment was essentially programming what I call laws into the physics engine to allow this environment to respond to environmental stimuli. And of course, as mentioned by multiple presentations prior to this, there's obviously a lot of challenges in designing in space. This project does consider a lot of them, but the main one that I'm focusing on in this presentation is radiation. And part of this project, you're gonna see a small icon in the bottom right. Because I'm starting at the molecular scale and I'm combining a bottom-up emergent approach to design with a more traditional top-down approach, at the bottom right, you'll see these icons which represent which visualization is happening at which scale. So there's 4 different scales: the molecular scale, the material scale, the human scale, and the city scale. So starting at the molecular scale, I was really inspired by cellular automata and John Conway's Game of Life. And basically, this is a simple 2D grid that has a series of pixels, and white is alive and black is dead. And basically, there's a very simple laws or rules that create these complex interactions, right? So if one is alive, if it's alive and has 2 or more neighbors, then it would basically continue to be alive by reproduction. If it's alive and greater than 3 neighbors, then it might die from overpopulation. So with a series of these simple rules, you can get these really complex, almost lifelike simulations. So I was really inspired by this work. So I decided to use a similar approach for this real-time environment, and I created a series of 7 algorithms that basically control this real-time environment, and to see how this computational chemistry in this digital system could potentially be used for a theoretical material. And so I started researching what materials could potentially be used for this. And at the time I came across graphene. It was a really popular topic at the time. And basically it's a 1 atom thick sheet that consists of carbon molecules. It's one of the thinnest and lightest materials, 200 times stronger than steel. It's flexible, can take any form. And more importantly, I think for this project, I was really interested because it could be layered into crystals and mixed with other materials to give it this kind of capacity to become this super material. It also can conduct electricity and heat. And so I was looking at this as kind of like the base molecule. And there's also, because I'm focusing on radiation, I was interested in how this material could potentially be used for controlling fluorescence and light. So although it could be transparent, you can also use carbon in order to create super black materials. And this is a super black material developed by NASA. So I started by working at the molecular scale and really trying to figure out what this molecule might, how it might react at this scale. And so I was looking at ideas that by layering these crystals together, and I started with a polyhedron structure that resembled the graphene molecular structure, and basically using a recursive algorithm to give it this kind of fractal recursive growth, and trying to question what might the molecular bonds be whenever it has these different types of molecules and compounds combined together in these layers. What might it mean for fluorescence? And I was really inspired by some work that was done at Berkeley and Stanford around, they basically are developing, using DNA to develop their own organisms, using synthetic biology to develop almost like a simplified or molecular computer that can seek out and destroy cancer cells. So all these ideas are kind of embedded into the spirit of this project and how we could potentially theoretically do this in space. And so what I ended up doing was realizing that there is a fractal-like crystal growth to this initial molecular form. So this is a very slow recursive growth, but I sped it up about 100 times so you can see what the effects might be. And you can see some small anomalies and nuances in this project in the output of the algorithm. And I'm not sure if you can see because of the screen here, but this value at this top, this variable of 0.05 angstroms, basically only changes from this screen by 0.5 in the next screen. And what you see is basically a very drastic change in the algorithm, or in the result. So the first rule was to grow, the first law, but the second law was basically to put some kind of limits into this system in order to make sure that it doesn't have this kind of cancerous growth and it can actually be used as a material for space architecture. And for me, this resembled kind of a cancerous growth or cancer cells under a microscope, where it has this kind of amorphic spherical form, but then on the surface condition, it has this more fractal recursive form. So the growth algorithm that I'm looking at in this project has 2 forms of growth. The very fast recursive, or the slow growing recursive growth, almost crystal-like nature at the material scale. And then at the overall form, you have this very slow kind of growth that reacts to the environmental radiation. So rule number 2 is to stabilize the system. Rule number 3, after this fractal molecular system was developed and it was stabilized, was to give it the implementation of what I call sight, similar to phototropism in plants. Basically, it's allowing it to now absorb or to direct itself towards incoming radiation, orient itself, and potentially grow towards it. And so I started looking at natural systems on Earth that we can start to think about how this reaction might be, and seeing that maybe this reaction in the case of growth, how it could potentially happen at this molecular scale. And in the case of this system, I decided that under high levels of radiation, the system would expand, kind of similar how the molecular bonds of water change depending on the temperature of the surrounding environment. I imagine this molecule could be designed in a way to allow it to expand during high levels of radiation, to absorb some of that radiation and to potentially protect any inhabitants that might be behind this material. And I thought about potentials for applications for 4D printing. So how you can maybe lay this material and eventually over time with environmental stimuli, it could basically start to adapt itself accordingly. And rule number 5 is self-assembly. Once you have these systems working by themselves individually, what does it mean when they start to come together as a whole? So I started testing out, and the little orange dot that you see resembles a vector that I'm using to simulate the direction of the solar radiation on the molecules. And you can see that they are reacting to the direction of it. And I started questioning what this might mean as an assembly of these objects and how might they start reacting together as a material whenever they're first focusing on their reaction to radiation within themselves, but then also how these agents then collectively start to have a more emergent behavior. So in this example, I started to realize it looks more and more like a coral kind of polyp nature, and it has this level of reflectance to it that also could potentially be programmed into the material. After having this material more or less at the molecular scale figured out, I started looking into how at the human scale, we could start to assemble or arrange these into a more of a hyperbolic arrays in order to basically create structures out of this material. And what you're seeing here is basically a Bezier curve that's being implemented in a real-time environment in order to basically create some kind of mechanism for arraying these molecules. And then here I'm basically using the array of the molecules on those lines in order to create different types of densities and testing it out in regards to this radiation vector, which in the moment is not linked to data, but the idea is that I would be able to input data into the system and it would be able to react accordingly. So this is testing out the different potential responses. And the tangent lines of this curve would basically be the vectors or the normals for where these molecules would basically be housed on this larger skeleton. And this is just, again, testing out how the larger skeleton might react depending on the different direction of this radiation input. So again, this would be at more or less the human scale. And what I imagine that this would basically look like when you look up close is, again, like this kind of coral-like polyp behavior at the molecular scale. And then with these exoskeleton, or with this structure in place, these molecules can again start to take on different forms and different interactions depending on the structure that they assemble into. So in this example, you're seeing that they're responding individually, but also they have kind of a collective awareness as they can basically follow this radiation input. So it's almost like this microorganism that you might see under a microscope is kind of the output that I was being able to generate. And then basically scaling up, it's very hard to program everything in the universe from a bottom-up approach. So obviously I made a lot of assumptions and jumps from the molecular scale to material scale. Again, I am not a scientist, so a lot of this is very speculative and design theory or design fiction. But at this scale, I really imagine this would act more or less like a ferrofluid material, where during high levels of radiation, it would basically be able to expand and react to that levels of radiation. And the idea is that whenever there's low levels of radiation, then potentially this could be more porous and open. And during high levels of radiation, it would then maybe close and build up into this kind of architecture. And at the architecture scale, I imagine this would then translate into a system similar to this, where you can see at the material level, it does have this kind of fractal-like recursive aesthetic to it. And then at the larger scale, if we were to zoom out from the architecture scale to, well, again, this is the architecture scale. This is a visualization of what I think that landscape, that reactive landscape might look like. Again, having these large porous openings whenever there's low levels of radiation versus whenever it has high levels of radiation, it can then close. And this project is, it's a satellite that is not on the moon or a different planet. It's in Earth orbit. So it does have different variations of radiation. So that's why it's important for this project to be able to react to those different radiations as it orbits around the Earth. So at the city scale, I imagine this would be a very kind of amorphic shape that can then slowly adapt to these incoming levels of radiation to better optimize itself in order to create a more efficient system as a whole. And these are just some diagrams explaining the inputs and the vectors that I was basically aiming to this system or this satellite in order to start to deform its shape. So it would slowly optimize itself over time. Again, these animations are sped up almost 100 times. So at the large city scale would be a very slow kind of adaptation, and then at the architecture scale would be much faster. And before I play this, this is basically a visualization of the entire research of the project. In this example, I'm not working in a real-time environment. The research was developed in a real-time environment. And this is my final visualization of what I think this system might look like based off of the research that I had done. Thank you.
Thank you, Albert. That was an amazing group of presentations. I wanted to bring in Madhu in a second to kind of like offer his overview of this. But what I would say is I thought it was interesting to my mind the way in which space became a kind of almost like a mirror in which to kind of reflect some of the concerns on Earth. I was particularly struck by some of the commentary that Luis was going on about how this could be seen as a sort of lens for thinking about, in a sense, the future as seen the past in the future and so on. And it seemed to me that there was a whole series of kind of very interesting kind of very contemporary Earth-based concerns that were being projected out into space. But I wanted to bring in Madhu to kind of to offer some kind of overview. I think what's interesting to me is that Madhu has had this opportunity over the years to reflect on the interests of architects in space itself, that he's been teaching himself a space architecture studio at the USC. And just to ask Madhu, how he sees this kind of, the interest in space among architects has been mutating and changing over the years. It seems to me right now that for various reasons, there is this obsession about space exploration. It's really capturing the imagination, but at the same time, it kind of reminded me in some ways of what the kind of the obsession that had always been there. I mean, I think that Albert's presentation somehow reminded me of 2001: A Space Odyssey, this kind of romantic, kind of fictional, speculative view of space that came right before the first mission to the moon. So we find ourselves in this kind of this world where the practical constraints of space somehow comes face to face with this more speculative science fiction outlook. Madhu, do you want to offer some comments on what you've seen today?
Well, Neil, what I get from the architectural community, to be frank, is the graphic visualization of your dreams, and that is very important for us as a species, because I like to tell everybody I meet these days that the faculties that distinguish us as a species is the ability to imagine, to be creative, and then manifest some of these wondrous things that you imagine and create, and then build and operate. I don't think any other species on our planet does that, at least not as well as we do. You can always say that in the oceans, I mean, you saw coral and so on, they do magical things, but but not with the deliberation and the precision with which humans do things. Now, I ran through, I thoroughly enjoyed all the presentations. For the engineer, the difficulties arise when you're posed with the requirements document, particularly when people are involved. Architects deal a lot with people too. So, when you build things, there is a factor of safety involved. And because the prime product you're protecting are people. And all the other stuff that you do is either in the periphery or secondary to when your life is threatened. And this is a lesson for all of us. When we start to draw and imagine things, we put people in the center. I think it's Alvar Aalto's statement, which says true architecture puts people in the center of your design. Now, when I saw some of these designs, I'm very happy to see the flow of ideas, and what I get from it are certain little particles of thought that allow me to connect it to thermodynamics, connect it to the fundamental physics, and how energy can be used to our advantage, leveraging the technologies we possess to make humans superhumans. I think there's a term we use nowadays. We say Homo sapiens cosmicus, that is leaving planet Earth and touching things we are not supposed to, at least not in the 20th, 18th, 19th, 20th century. We were not allowed to do some of these things, and now we freely engage in it. It's about the development of the human condition. It's always opening up new vistas for human development and consciousness, expanding our consciousness beyond the little fragile thing we call planet Earth. And that's my opening thoughts. Please go on.
Yeah, thanks, Valerie. I get the sense that what space offers is a kind of a space of the imagination, of exploration, kind of somehow takes you out of our preoccupations here at some level and allows you to express that kind of imagination in a kind of new way. So that's the feeling that I got from today's presentations. Maybe I could just go and move on to particular questions, because we've got a whole series of questions here on the chat. And just say if anyone else wants to go and put them in, please send them either to the Bilibili or to the YouTube link. And first, this is a question from Victoria Barbo, first initially addressed to Luis. Cosmology is a very interesting and pressing topic to look at and to think about. What is the future of knowledge when not only bodies but minds are leaving Earth? Redefining the relationship between mind and matter, which I think is a beautiful question, especially, I guess, in the context of COVID, where to some extent we've been leading a kind of disembodied existence. I mean, even especially now, we've discovered the kind of potential communications we can have, where we have some people in China right now, some in Europe, and some in the States, and so on. This idea that somehow we can kind of, in a disembodied way, kind of communicate. In fact, also, we are forced to in many ways. We had a presentation a few weeks ago by Sumin Ham, where she was running a project in Scandinavia from Los Angeles using AR as a kind of an operation. And it seems to me that we have there's a new kind of configuration now. We have to sort of think about the difference between the body and the mind. So maybe that question for Luis. Cosmology is a very interesting and pressing topic to look at, to think about. What are the futures of knowledge when not only bodies but minds are leaving Earth, redefining relationships between mind and matter.
So I'm going to try to link both Arisa and Selin into this one, because both of their projects also were thinking about the relationship of the body to being in space and what is necessary for it to be efficacious, but also for what is necessary to keep it alive and healthy and comfortable. And part of this whole contemporary setting we've got with our Zoom meetups and our virtual drinks and our perpetual lockdowns has only, to me, from my personal experience in this room, shown me the absolute necessity for keeping the body healthy and the body happy, and making sure that the environment we put ourselves in is one that is actually suited to our physical self. That was what me was the most interesting about Selin's research. How you can try to create these social environments that nurture you as a mind, but because your mind and your body your mind is embodied, these environments that nurture your mind are necessarily physical environments.
Selin, do you want to comment on that?
Luis, I don't know how I know your name, but I may have seen it in an email or something like that. I enjoyed your thoughts. They were quite complex, and I always thought the term cosmology was mostly employed in the realm of astronomers and physicists. I did not think of cosmology in terms of chronotubes and not even in the anthropic principle, I think that you mentioned a little bit. But what I was reminded is when you showed the repository of information in the past, the present, and the future, I was reminded of Alberto Perez Gomez. Neil, do you know that name?
Yes.
Yeah. Yeah. And, he mentions that we have never, ever thought beyond categories. And then I look at the works of people like Gaudi and others, and you're going, oh, this man he's blowing up grenades all over the place, because the moment you try to put him in a category, he just defies the principle. And so I think it's a very interesting thought that you do. And I've always thought, again, this is a very narrow view, but there were two important instruments in our probing of the universe, Luis. I love the idea of your telescope looking outwards, but if you look at the history of technology and science, you will notice, and I think Neil probably knows this too, there was a big fight in the Royal Society between Robert Hooke and the young Newton. Robert Hooke produced micrographia, and he was using the microscope to look and document the intricacies of life. And Newton comes along and produces stuff. Of course, telescopes had already been used, but Newton produces the reflecting telescope. and talks about the others, outside of planet Earth and so on. And sometime Robert Hooke looks at Newton and says, have you touched any of these things? Or just imagining. And there's a strong connection or a dichotomy between the way we abstract and think about things that are out there versus the life scientist who explores the depths of things that she or he can manipulate every day. So that was just a thought when I saw your designs. But please go on.
Yeah, thanks, Madhu. I think the question of kind of reflection and reflecting the microscope and so on, the idea that somehow that space itself can become a mirror, which in Latin is speculum, a speculum in which you can speculate about things. So space becomes a mirror to human activities. I think this is what kind of somehow grounded all the presentations today, is that it was allowing them to kind of think about very, in some ways, pressing matters of today. And I've got a question here for Albert Elias, because I think one of the interesting kind of comments, Albert describes himself as an information architect in a way. I think that's one of the things that has maybe, in terms of our own paradigms, the shifting paradigms, the idea that somehow we're no longer just simply talking about form for the sake of form, but form that's somehow informed by some performative questions. This is, I think, to me, fundamental, at least to what the ideas, what Anaximander was talking about morphogenesis. It was also, I think, grounding the work of Albert Elias. So I want to bring a question in from Marina Rodriguez das Neves to Albert. First of all, this is a super interesting job. I was wondering, how could the emergence of the system be categorized in that way that they reinform from the molecular scale new growth logics? Also, how can we name this process of differentiation? What kinds of new models of beauty are these speculations creating? I guess, maybe over to you, Albert. Make of you what you will back those questions.
Yeah, it's a very hard one for me to answer. I think really the whole idea of the project, when I'm thinking about it, is design at the level of the molecule. And for me, it's like when I'm looking at a material, whether it's a computer, whether it's the table that I'm looking at right in front of me, I'm always thinking about, even though I don't know the physics, I don't know the science, I'm always thinking at the molecular scale and how that transcends into what our experience is as humans. And for me, I really don't see a difference between the organic and the inorganic. For me, it's just a continuous spectrum and a blur. And I'm not sure if I'm answering your question or not exactly, but for me, the ability to program and test out simulations in the digital environment and kind of get these unexpected results, which I sometimes refer to as these digital monsters. And then how do you tame that monster and then, make sense of it and rationalize it? I think that kind of goes back to what Madhu was saying about how, the humans are imaginative creatures, that it's how your perception of reality versus the actual science. So I think what's interesting about this workflow is I describe as going from more of a hybrid of a bottom-up emergent process with a top-down logic, is that you meet somewhere in the middle and then try to rationalize whatever you're getting from this bottom-up approach. So I would imagine, I work with scientists, and but I don't understand the science myself. So I'm usually typically doing the data visualizations. But I would love to learn more about the science, and then maybe with a little bit of practice and education, I would be able to answer that question much better.
Yeah, Albert, when I saw your work, I thought about, and you mentioned synthetic biology. I'm sure, even if I don't understand it myself, but if you look at the work of Craig Venter, you'll see what the envelope is in synthetic biology. We still don't understand life for the life of it, but we are able to put the molecules together or change the structure of the DNA to produce synthetic products that still live. and do the things we want them to do. Again, without knowing how to create it, we are able to manipulate it. I think you may recall the words that Dick Feynman wrote on the blackboard one time. That which we cannot create, we do not understand. And it's important because he says that in many of his lectures in quantum mechanics as well. And you know, I would never ever put that little note on the end of your slide, which is, I'm not a scientist. Everybody is a scientist at some level or the other. And that's what I mean by curiosity and imagination. And I could tell your imagination was flowing, you know, flying off the handle for most of that presentation. Now, you know, when I looked at your work, I saw crystallography as something that you want to explore before fractals, you know. Benoit Mandelbrot and Julia such and so on are okay. But again, to become real, you want to look at crystallography in biology. And the Nobel was awarded to the sitting president of the Royal Society. His name is Venkatraman. Of all things, a guy from India who's running the Royal Society. And now Neil's going to feel jealous about that, but that's how it is. Anyhow, he explored the structure of the ribosome. And you want to look at what the ribosome does inside of a cell. It is the most incredible machine that generates a variety of different proteins, and a spectacular thing to do. I don't want to take too much of your time, but I'm sure there are many more questions, Neil.
Yeah, what I'd like to do actually is there's some questions in the chat, but I'd like to get the panelists themselves to ask each other questions. I mean, this is the opportunity we have here of spanning the globe, literally. But first of all, I mean, while you're thinking about that, I want to ask, just bring in Selin here to go and pick up on to what Luis was talking about in terms of the body. Do you want to offer any reflections on what Luis was talking about?
Hey, I really enjoyed all the presentation, first of all. So what I was thinking is, before I started this research project, I was drawing comics, and I was like thinking about a lot about the songs from the end of the 60s and beginning of 70s, which was about space. And they were all like, I was thinking about Elton John's song, Rocket Man, and it was saying, there was this part, it was saying, Mars ain't the kind of place to raise your kids. So when I started to think about these kind of things by relating to human body, human mind in itself. So it's not really, I cannot think them separately, because if we're sending humans to Mars, I start to think about realistically, like I suddenly think about feelings and emotions and senses, and because it's about creating a home in a way, because they're gonna stay there and they need to make that place home. And I really started to ask, like, how do we call a place home? And it's really it is really about creating a belonging and that sort of things. And it's just like, and it's maybe about bringing a little bit of nature. So it's not about like home away from home, but it's a bit like nature away from nature. And our bodies really evolved in nature. So we really love to feel the sense, like the feeling of wind on our face, and we're not gonna feel that on Mars or on Moon. And how would that affect our like mind? And I mean, it's affecting our body, but also it's affecting our mind, and we're not gonna be able to feel all those like stimulations, and it's gonna really affect our psychology. And it was really interesting for me to like think about all of these things. So I don't think that we can. I mean, people are going to go to Mars physically, we really need to think about the human factors. I mean, yeah.
Selin, what I found in your work is your gravitation towards wrinkles. And I think you may be familiar with that our brain is one heck of a wrinkle. And if you look at the art of protein folding, that is also about wrinkles. How do you tie things up together in a compact place with all the information that you need and that you can release at the time you need it? And you'll see that kind of information being tied up into knots and wrinkles. And this is a fact of nature. And I found that very interesting that you touched on it. And of course, many of the things that you put down for humanity is not applicable for the astronaut. And I think you know this. If you've met them, you probably know they are a subspecies. They've been trained and grilled in such a way to react in certain ways. And we know that in the past too, the way they've conducted themselves during anomalies and go to the depth of their training. Because when you look at some of the things that have happened and how they reacted, it tells you they're not normal humans, and they're trained that way. So, so that's what I had to tell you about. Again, I wanted you to think about biology from both the philosophical point of view, which you have done pretty well, and also from the technical point of view. You know, one thing that differentiates biologists, just like during the earlier, developments of the split between the physicists who imagine and try to make sense of the world versus the biologists who deal with concrete materials and see how things evolve. The fact remains that either of those disciplines still don't know what the heck is going on, either in the bigger universe or in the smaller depths of the molecule. And so when I saw some of your visuals and some of the way you congregated the habitats, I was thinking about termite mounds and ants and how they build their stuff out. And that was my thought about you, Selin.
So maybe, Madhu, I can just ask you another question that's coming out of the chat here. I mean, so Luis has made the comment about this. I'm not sure it is our job to populate the universe, but we need to learn about it. And I think, I just wanted to get you to reflect on, just to go back to this question I asked you before about reflecting on your time working on space architecture. I think that we've had an enormous shift in terms of attitudes. The idea initially, I think, that there was going to be an apocalypse and space would be the only kind of place where we could find some refuge from this nuclear holocaust that was going to happen. And now, of course, we're discovering that actually the radiation in space is far more severe than the radiation on Earth. But what is kind of interesting is that the dream persists, the dream of kind of colonizing other spaces. If you were to sum up the kind of the shift in attitudes that you've experienced among students of architecture, looking at this kind of question of space over the years, have things shifted, or are they still the same kind of dreamlike aspirations we had many years ago?
I think they have shifted a lot because of the tools we use in the architectural profession, Neil. I was drawing with my hands, pencil on flimsy on paper, and doing chiaroscuro and so on to color stuff. And now you do this on Photoshop, and you have a variety of packages like the ones you saw today that allow you to do magic without ever without ever straining or messing up your clothes. So there is a definite shift in how we think about what is possible. I also think not all cultures do this, Neil. It is only, I think, it's predominant in the West, where we have this sense of freedom, ultimate freedom, and that space, as you mentioned earlier on, is literally vast and open and engages our freedom of thought and expression like no other venue that we know of. A lot of people ask us, why aren't we exploring the depths of the ocean, which is so much closer to us? Why are we going out there where, as you said, the radiation will kill you in a matter of minutes? And I know this because my co-author on the book was director of radiation medicine at Palomar Medical Hospital. And he would tell me stories of radiation poisoning. And he would tell me it is the worst way to die, worse than the bends. And so radiation is not a joke. And I was sitting next to one of those celebrity astronauts the other day, and a presentation came along, and it literally made us feel terrible. The way you lose your cognition, the way when you're asked to do something, you're even unable to pick up the right switch if your brain is shot. And that's what radiation does to you. And yet we want to go out and participate and play among the stars. So I think it is something that is ingrained in our model of governance and what we teach our children about the value of freedom. And that's where I would leave it at. Maybe there are other ways to think about it, but I can tell you it's not common for all cultures.
Yeah, but just one thing, Madhu, I know from you is that one of the comments you've made in the past is that the old-fashioned NASA view of putting boots on planets is kind of giving way to a different sort of vision of the world. And I also noted the fact that when you were talking about moving to Mars or the moon, that you would not use the word colonization. That was kind of like, so we have this kind of interesting kind of issue about appropriating space now, which is becoming a super important sort of question. And I think this was raised by two of the projects, the team from Shanghai and also by Levant, about the question of mining. So, does space just become a resource? I mean, it seemed to me that was kind of quite a controversial sort of issue. Should we treat space simply as a kind of space where we could extract mineral resources, or what? So maybe I could just raise that sort of kind of question about colonization as also an issue.
Yeah, well, I think some of you may be familiar with this, but in the last 4 years, the United States has been quite aggressive in formulating plans for our future in space. And two documents, I mean, there were several documents during the last 4 years, which included augmenting the space policy of the United States. A few days ago, the final document was published about the policy of the United States. I still have to scan it, but it's clear with the space policy documents issued by the White House. I think there are 5 of them. And it's clear that the term that is used often is that space has become contested and congested. And this may be correct in some ways. You want to look at it from your own lens, but a separate document came out called the Artemis Accords. Are you familiar with this, Neil, or some of you?
I'm not.
oh, you need to read that, because it was, again, an aggressive push to go out and give the commercial industry a shot in the arm and says, you go out, get what you like, and it's yours. And this caused quite a big brouhaha in the international community, because there are some laws and resolutions in the past. One is called the Outer Space Treaty. There's another one called the Moon Agreement, which tells you that all of these things out in the heavens belong to us all. We call it the common heritage of humanity. The specific term is common heritage of mankind. But looking at it, it's my opinion, it's always been the case. I think you all know the golden rule, not the one from the scriptures, but the one from our own baseball manager, who said, the one who has the gold make the rules. And the way it works out is that established nations and spacefaring nations who have the experience will go out and do these things first, and then the rest of us follow. However, we live in a multipolar world now, and there are many capable players, and they all want to voice their opinions. So the idea of going out and mining something or doing something is not a unilateral issue anymore. It requires us to be players. I think Friedman talks about it, about the flat world model. And there are many, many players, and we want to engage them all.
Maybe I can bring in so there's two teams that were talking about mining, Levant and the team from China, to offer some comments on that. Does it worry you that this kind of issue of mining in space? Is Levant there?
Yeah, no, I don't think so. I mean, I think that the ethical point is interesting, but I try to see it more as in conjunction with micronation trend, and where these could become small micronations of their own, somehow self-sufficient. And I think that's the reason maybe I used colony rather than something else, because you go there and you try to make it self-sufficient and then leave. Obviously, this also has negative connotations in history of some countries, but because where we're arriving at this point doesn't have any inhabitants, maybe that could be isolated, like that historical connotation, just be looked at as a material, hence a small ecosystem resource. But I'm not. I mean, I'm open to.
Okay. Well, maybe
Luis, well. I just wanted to mention this to Neil too. When we wrote our book, and you'll see that the difference in the first and the second editions, Neil. In the first edition, we used the term colonization on the title. In the second, we were admonished and told them to make it settlement. So since then, we've always used the term settlement. And Neil and his buddies from the UK are partially responsible for this colonization part.
Yes, absolutely. No, you're right. But okay, let me just kind of try and bring in the team from Shanghai, because I think what is astonishing now is that China is making such a huge effort, and it seems to be, from what I pick up on WeChat and elsewhere, that actually space exploration in China is something that is really a hot topic right now. So maybe I can bring Dan in to sort of comment on the kind of attitudes in China, especially around the architectural community, to the possibility of space architecture and of the exploration of the space. Dan, would you like to say something?
Oh, yeah. So you're questioning about the issue about the space architecture and how architects view this point, right?
Yeah, I'm interested in China, the situation now, and because it seems to be that there's a lot of excitement in China because China's now become a significant player, shall we say, in space exploration. And how is that kind of how do you see the attitudes towards space in China, and especially among the architectural community? I mean, is your project very unusual? Are there many projects in China looking at space architecture, or over to you.
Yeah, actually our project is about a international competition, but I also say some like architect in China, the drawing kind of competition, which linked, which maybe like more about the exploration of the space architecture, because we the starting point of our competition, we also read a book from a professor in China. He's doing like research specifically on the space architecture, meaning like more, I think more professors in China, they're paying more attention to the exploration of the space architecture. And they also kind of want to analyze all the history of the space architecture, not only in China, but also in Russia, because they do this kind of research maybe earlier than China. And also, China is also a big country that maybe more like we have lots of specialists in the space. I mean, like scientists doing research more about this part. And also because I think the issue is about the lacking of the resource, because in China we got a huge population here, and but the resource is very kind of limited. So I think more like scientists, and also I think also architects, we need to think more about how we can explore more about the resource in the space. For us architects, I mean not scientists, we may think about using more like methods related to architecture design, and more specifically I think it's like space architecture. So I think that's the issue we are facing in China, and also more like professors are doing more research in this part. So
maybe just
Neil,
ask your
maybe I can inform you a little bit more about how we think China is moving along, specifically with the space program. If I were to look, not with jaded eyes, but just rationally, along the spectrum of space programs around the world today, China is the only one that has and maintains a cadence and a schedule that works like clockwork. And they've been moving very steadily. And as you know, China is about to bring down lunar samples that they just acquired at a very specific region of the moon, and that is important for settlement. And the strategy that the Chinese space program has put in place is unlike any other we know, and not the Soviets, not the US, but as I mentioned, the step-by-step approach is impeccable, and something to be something to admire. And they have, you may know, that from absolutely nothing. I don't know how far Dan knows about the history of the Chinese space program, but Quan was a student at MIT, one of the brilliant students, and then he came down to Caltech and worked under von Karman when all the story of McCarthyism and communism happened, which which we are known for from time to time. We have spurts like that. We're going through one of those now. And we sent him back to China. That was unbelievable. He goes there, becomes the father of the space program, and look what we have now. And the United States of America is famous for doing this. And we generate and open up the minds of people around the world, and then let them do their thing wherever they go, out into the cosmos.
But Matthew, just one question. My impression of the Chinese space program is it's a little secretive. I mean, we really don't know much of what's going on there. NASA, by comparison, I mean, one of the great things about NASA is they make their materials available, open source. I mean, all the images from space are, you can use them without, there's no copyright on them and so on. How do we know what's going on in China right now?
Well, don't just blame it China. It's the same with Russia. It's the same with India. They don't talk as much as we do in the West, where everything is open and transparent. And Dan, did you want to say something?
I think it's something related to the government. It's, you know, because I totally agree with what you said about because, you know, sometimes they don't let us know everything. Not only, you know, not only American or Russia, but also with Chinese. We don't know everything, but we just, you know, I still remember that the first time when I say Chinese government, they launched a rocket, everyone was like sitting in front of our TV to just say the, you know, the TV cast. But at that point, we don't know the procedure, but we only know the final result is, you know, kind of fantastic. But I know it's happy. We were happy to see the result, but also the thinking about the procedure and also the future is like more important. So I think maybe the discussion should be focused more on the research maybe.
Go ahead, Daniel. Yeah, no, we want to wrap things up fairly soon, but I just want to give Aries and maybe Jack a chance to kind of comment on things. You've been waiting patiently in the background there. It'd be nice to see you. I think what's great today is we've got a real sense of what's happening all over the world in terms of the exploration, and it was a real insight to the kind of architectural imagination that's been going on. But Aries, do you like to say something, and maybe Jack comment?
I would like to say project have a lot of different perspectives, which I really like, very interesting to explore. There's so much things for us to explore yet. And yeah, I think there's, really enjoy it and just don't know.
Okay, I don't want to push you under pressure.
In Aries' visualization, the Vitruvian man came across as an important scale in what we create. And if you look at the human standards document, there is one called the STD 3000 that NASA used to keep, but now we call it the Handbook for Manned Space Systems. If you look at it, it's kind of comparable to Ramsay and Sleeper. Are you familiar with, Neil, did you use that in your works? All of us in American schools would use the architectural standards document when you wanted to plan or design. And it had very clear anthropomorphic scales in which you engage your design principles. And similar to that, but very, very much, very less rigorous is the STD 3000 that NASA uses in the human manned systems work. Because after all, we are only 60 or 70 years old compared to civilian architecture, which runs a few thousand years old. So you can expect that we still don't know much about conditions and volumetric analyses. We are still learning that. But I got that impression from Aries' work that you are really focusing on a human scale.
Well,
Yeah.
okay. Madhu, one thing I'd say, I'm a little skeptical of those universal models. I mean, there's always a man, right, rather than a woman, and it doesn't necessarily take into account different sort of cultures. I think one of the interesting common situations we're in right now is I think that JFK, his vision back in 1962 was to send a man to the moon, right? A man. And now we are about to send a woman to the moon, which I think is, and it's great that we have so many female speakers on this presentation today to go. So we are a more open, inclusive society in many ways. Maybe, Jack, I know you're still there, but it'd be great to kind of just get your reflections on today's presentations. Jack?
Yeah, all of these presentations were really beautiful. Thank you, guys. There's been some discussion in the chat, just how do we bridge our work as designers and speculators to the actual science. And I think that the bridge is already there, that we come up with all these ideas and we don't have all the answers, but a lot of art and design work informs the direction in which science is undertaken, and how artists like Rick Guidance could take direction from NASA, but come up with beautiful, speculative, early concepts for what we think of now as retro sci-fi that's really defined our generation's understanding of what these things look like and can be, and how he really just drew a bunch of greebles on top of some cylinders and called it a day, but how that's really sparked our imagination and carved the way for real science.
Did you mention Rick Guidance?
Mm-hmm.
Interesting. Okay, good. You know, they were the early visualizers of future in space. Jack, I found your lava tube story interesting, because if you look at the current literature, and that is the last 10 years, you will notice that there was a man from Japan by the name of Junichi Hirayama, and you know, during the Selin mission that Japan did, was the first time they noticed an aperture on the lunar surface, which then quickly was looked over by the Lunar Reconnaissance Orbiter, and we all first figured out that there are holes that allow us to go into lava tubes, and you said the term skylight. And so it was Harayuma who first mentioned this. And now, if you look at our own, the second edition of our book, I had a hard time visualizing how to go inside a lava tube. And the only way I could draw that was to show a large drill jig sitting atop a supposed lava tube, and you drill down and you go inside. And now we know that you can walk into a lava tube. And so there is a whole school, including yours truly, that we think lava tubes are the easiest places to go to if you want to think about permanent settlement, for exactly the reasons you mentioned, Jack. You are away from radiation, away from thermal diurnal temperature cycles. I don't know who thinks they can design anything on the surface of any place and survive the huge diurnal cycles. On the moon, it's 300 degrees between daylight and nighttime. On Mars, it's less, but still not bearable. And lava tubes are the places to really consider setting up home. And hopefully, hopefully we'll see many more visualizations like yours. Thank you.
Thank you.
So I think, thank you, Jack. Thank you, Madhu. I think we better wrap things up now. I think what we see today, I want to thank all the presenters, because I think we've had an incredible range of different sort of, contributions today, and thank Madhu too for his fantastic feedback and things. But above all, I think what we've seen actually is what architects can do in terms of the architectural imagination. I think that's something very precious. I mean, whether these ideas are practical or not, I mean, architects are always dreamers in some ways, but I think what we do have is this astonishing imagination. So I'd like to thank everyone for this great series of presentations.
And you want to mention Levant. I liked his visualizations, and when I looked at that image of circles upon circles, in biology, in the inner ear, there is a
eardrum.
Inside of the eardrum. It's
Yeah.
called the cochlea. Levant, you want to take a look at it. It pretty much tells you why and how we are able to balance. In the it's within the vestibular system, and regarding mining of asteroids, these are all very advanced works we can expect to happen once we control energy, Levant. And I think there was a question from Rincon asking what is the envelope that humans are pushing in real space. The problem that we have is energy. Most of the works we do right now either are done close to the sun in what we call the Goldilocks region, where water is available to us and the temperature is not too bad. The moment you move away a few 100 million miles outward from the sun, sunlight starts to dim very, very rapidly, and we got to go nuclear. And there's a great deal of discussion and debate about nuclear power. Again, it's an area where the United States has opened the doors now, not only for civilian use on planet Earth, but also for space. And we expect to see some advances in NASA's nuclear power work. So watch out for that. The important thing, again, is if we can control and create energy, we can do a lot of things. And this comes to you not only from the space industry, but also from the aeronautical industry, where I think Ben Rich, the successor to the great Johnson, Kelly Johnson, who built the SR-71, he once mentioned, you should not be fascinated by aeronautics. If you give me enough power, I can make a brick fly. It's true in space as well. If we can somehow master and tame energy and power, we can do magic anywhere.
So anyway, we need to wrap things up. This is fantastic, Madhu. Maybe if you'd like to suggest some links that we can put on our Discord channel for where we can find out more about space architecture, because I know there's a lot of organizations which a lot of debates going on. It's really a question of access, and I'm sure that lots of architectural students would love to hear more about that.
The first one that you want to go to is the spacearchitect.org. We put up we have a bibliography there. You go on the URL, spacearchitect.org, and then you can see what we are up to and all the things we are doing. And then, of course, there are many conferences. There you go. I think Gustavo just put it up. You'll see all the mischief we create there. And, I want to mention the fine words from Freeman Dyson, who passed recently. He was asked, what's happening with going out into space. And he said, we've been looking out into space for hundreds of years. It's black, it's dark, it's cold. What are we waiting for? It's our job to go and make it beautiful. Okay.
Okay. Good.
Thank you all. Did
I
we
just
cover them all, Neil? Did we?
I think we want one thing. Just one final thought. I think for the first time ever, we have an astronaut becoming a politician. Do you want to say something about that, Madhu? We'll just as a final comment.
Well, there's not just a little bit about this astronaut who's become politician and a senator. The reasons are, if you look back at the history, his beautiful spouse was, she was in a terrible assassination attempt. And so then he went on to win in a very contested election. I mean, in the state, but it was a very smooth win for him. And I think you know about both Mark and Scott Kelly. They're twins, and many of their works are still being researched because this was a golden chance for us to see if there are changes in their DNA structure, having spent a year out in space and so on. So those kind of researches will go on forever. But I'm glad we always have an astronaut in our Congress and in our midst in the governance model, which brings me to our presentation in a week on Saturday. We'll have Professor Reisman. I'll interview Professor Reisman because he has joined USC and retired as an astronaut, and we'll be discussing things about simulators and space architecture. I think I sent you the program, Neil. Please share it with your wide audience, and we'd love to engage as many people.
I'll put it on our Discord channel. Thank you, Madhu. Thank you, everyone, today. This has been super inspiring. I think what we found out is that the architectural imagination has no bounds. We are out there and producing some wonderful stuff. Let's try and revisit this topic sometime in the future. It's certainly a very exciting time to be alive for those interested in space exploration. It's an extraordinary moment that we're about to witness. So,
did I say the same thing about G.K. Chesterton in the last gathering, Neil, when I said that there are no rules of architecture for building castles in the clouds? And he also said that there is a road from the heart to, what did he say? He said there's a road from the eye to the heart that does not go through the intellect. And in many of these things that you see, visualize, we see that. We want to do things that are that is impossible using conventional physics. And you know what? We do them. We really do. And you go like, whoa, we could have done that. If only we had, we could have done that. You saw the Starship a few days ago come belly flop and come down and go up in a blaze. That huge big rocket ship that Elon Musk is building. A lot of people tell you it can't be done, but you know what? There are some young people out there doing it right now, today. God bless, and all of you have a good.
That's a wonderful point on which to leave. Thank you, Madhu, and thank you so much to all our presenters today. Thank you. Thank you.
Okay,
Thank you.
Bye-bye.
Thanks very much, everyone. Bye-bye.
Bye.
Thank you.